to this computer. All right, and we'll go ahead and begin. All right, we got a lot to talk about today. This is an assortment of topics that I've tried to put all in one lecture. We'll be talking about a few operators from C that maybe you didn't notice or you didn't get a chance to cover in Java. I'll try to quickly cover a bunch of statements in C and especially conditionals. And then at the end, we'll talk about functions in C. We've been using all that stuff so far, but kind of informally. As usual, if you have questions as I'm going through this, hopefully I can hear you. Just speak up and ask your question and I'll try and answer it right away. Don't worry about interrupting me. I can probably handle it. All right, so like I said, this is what we'll be talking about today. The first thing I'll do is I want to introduce a few operators. Some of them are specific to C, and some of them you had in Java, maybe you just never used them. Here I'm listing a bunch of operators, mostly ones that we already know, and I'm listing them in precedence order. So this first little line is the highest precedence operators that we've used so far, post-increment and post-decrement. It's worth remembering that unary operators that come after their operand, those tend to be in the highest category. The next category is usually stuff that's unary operators that come before their operand, like pre-increment and pre-decrement, or later we'll see like the logical negation or logical not operator. Those ones in red, go ahead.
I don't know if you intended on sharing your screen, but I can't see anything that you're sharing if you are.
Ooh, I pushed the record button and I might have forgotten to push that. Thanks for catching me. Thank you. All right, so is this working now?
Yes, sir.
Takes a whole class to run a class. All right, so this is what I was talking about a moment ago. This is our table of precedence. And I won't repeat this, but the red ones are the ones we're going to spend a little bit of time on today. Sorry, I'm just trying to get this part out of the way. All right. So these are some we'll cover. We'll also cover logical and logical or, which you already know about, and the ternary and comma operator. And ternary was there in Java, but you might not have got a chance to see it. We'll start with the size of operator. This was something we really didn't need in Java, but we're going to use it all over the place in C, because often, so what it does is you give it a thing, and it'll tell you how much memory it takes to store that thing. Like I'm showing here, it works on types. You can ask what's the size of an int, and at least on the common platform, that'll evaluate to 4 bytes. You can use it on variables. You can ask what the size of a, variable is. Sorry, I'm trying to mess with the pictures here, so it's just my picture. But when I click it, I get someone else's picture. All right, you can ask it for expressions. So for whatever that expression evaluates to, it'll tell you the size of the memory needed to store that. Sorry, I know you probably can't see it, but I'm just trying to move around the little copy of people's pictures so it's not covering the slides as much. Here, let's do that. All right. So you don't get to see my face, but at least you get to see the whole slide. Sorry for the delay on that. When you use size of, there's a special type that it evaluates to. It's called size underscore T. A lot of C types are like that. They have a T at the end, and that just means it's a type. So size T is the type used for storing the sizes of things in memory. On the common platform, that's really just another name for unsigned long. But for whatever platform you're on, if you need to hold the size of a thing in memory, they've got a specialized type just for doing that. If you want to print size of values, there's a conversion specifier for that, %ZD for that. And you can also use that, I don't know if you'd ever need to do this, but if you needed to read input that was a size of something in memory, you could use that same conversion specifier. Like I said, we're going to use size of all over the place, because often if we're storing something in memory, we need to know how much memory it's going to take to store that thing. So that was the size of operator, especially when we start doing memory allocation ourselves. That's going to be awfully handy. Here's an operator that is, in the interest of completeness, I'm going to talk about it, but it's probably one of the operators you're going to use the least. The comma operator. In Java, they don't even have a comma operator, at least not one that works like this. In C, they defined a comma operator mostly so that if you have two expressions you want to evaluate, and you've only got room to put one expression, like if you're writing a for loop or something like that, it's got slots for a conditional expression and an increment expression. You can use this comma operator to separate two expressions and put them in a slot that's made for just one expression. What the comma operator does is it takes two expressions, one on either side, it evaluates both of them, and then it evaluates to whatever the second expression was. So it does whatever expression's on the left, but then it evaluates to the one on the right. Here's some examples down here. I make a couple of variables, and then I've got C equals A comma B. So like I said, it evaluates the expression on the left, and then the expression with the comma in it evaluates to whatever's on the right. So you might think this sets C to B, which would be the case, except if you remember the precedence chart I showed at the start, the comma operator was really, really low precedence, even lower than equals. So what this expression really does is it assigns A to C, because that's the whole expression on the left, and then it evaluates B, but doesn't do anything with that value. We don't store it anywhere or anything like that. If you wanted C to get assigned to B and you wanted to show off using the comma operator, you could do it like this. You could use parentheses to force it to evaluate both A and B, and then use the value of B to set it to C. Really, the only time I think you would use this is if you had side effects. If you're post incrementing A and B as you did this. And again, normally you would use this just in places where, like in a for loop, you had a slot that could hold one expression, but you needed to do two things in that slot. So you could have two expressions separated with comma. So whereas comma, I don't think is a terribly useful operator, this next one I find awfully useful once you get used to it. The syntax for it is a little cryptic. It was there in Java, but I find that most students in C class, they haven't seen it when they get to, most students in C class, they didn't get this operator. It wasn't taught when they were in Java class. The ternary operator is called the ternary operator because it has three operands, and most operators have just one or two. Down here is how you write it. It kind of comes in two pieces. There's a question mark and then a colon. And the three operands are in between those. So the first operand is to the left of the question mark, and it's a conditional, it's a test. For the ternary operator, when you use it, the compiler writes code to evaluate that test, and then it uses one of the remaining expressions, either expression 1, which is between the question and the colon, or expression 2, which is after the colon. It uses one of those two remaining expressions based on how this test goes. If the test evaluates to true, the compiler evaluates this first expression, and that's what the whole thing evaluates to. Otherwise, it evaluates the second expression, and the whole expression evaluates to whatever that second expression evaluates to. This works kind of like an if statement, but if statements work on statements. It evaluates a conditional, and then it evaluates, or it executes either the statement in the body of the if or in the else clause if there is one. Here, all the players are expressions. I've got some examples down here of how you might use it. So if you wanted to do a test and then pick one of two expressions, like this first example, it's kind of doing the max operator. It tests, is A bigger than B? If it is, I want this whole expression to evaluate to A. Otherwise, I want it to evaluate to B. So it's picking either the A expression or the B expression based on how this test goes. So as a result, C is going to get whichever is bigger between A and B. This can work for numeric operands like I'm doing up here. It also works for strings. I'm showing down here, I want to print out a message like that'll be so many dollars. But I only want to say dollars if the amount is more than one. If there's just $1, I want to do singular. I could do this with an if statement and two different printouts, or I can choose between the word dollar and dollars based on whether X is 1 or not. And that's what I'm doing. When I print out this, I'm going to print a number, and then one of these two words based on how this expression goes. If X is 1, I'll get the singular dollar. If X is not 1, 0, or more than 1, I'll get the plural dollars. So you see how that's kind of like an if statement, but it's built right into a slot made for an expression. You can do this same trick in Java, but like I said, often when people get to this class, they haven't seen this in Java. That's all about at least the first few new operators I wanted to talk about today. I'll try to sneak in uses of the ternary operator when I can, just to remind you about that. It's kind of handy if you don't mind the weird syntax. Any questions before we move on to a slightly different topic? All right, I'm not hearing anything. So the next little batch of topics is about type conversion. First, let me say, just like Java, type conversion kind of happens in two cases. It can happen explicitly. If you've got a value of a particular type, like float or short, and you want to tell the compiler to write code to turn it into a different type, you can tell the compiler to do that explicitly. And that's what a typecast is, just like it was in Java. There's syntax in C for saying turn a value of this type, or whatever type it is, into this other type. We'll talk about that, but I think in C, the more interesting topic is the implicit type conversions. Even if you don't use a typecast, even if you don't tell the compiler to convert a particular type, it'll do it in a lot of situations. It'll decide you must have wanted a typecast there. The thing that makes C interesting is it'll let you do implicit type conversions in a lot more situations than Java would. We'll spend some time talking about that because since C will let you implicitly convert types all over the place. Again, lots of places Java wouldn't let you do that. To understand what our code's going to do, we need to kind of understand what implicit type conversions the compiler will make for you, again, so we can know what it's going to do with the code that we're writing. First, we'll talk about the explicit type conversions because those are kind of simpler. Just like in Java, an explicit type conversion is a typecast. The syntax for it is pretty much the same as it is in Java. I've got an example of it up here near the top of my slide. If you've got an expression, and then once the expression is evaluated, you want to turn it into a different type, you just put the destination type inside parentheses, just like you would in Java, and then the compiler will convert that type, the resulting value of the expression, to whatever destination type you put inside the parentheses before you use it. So here's an example on the next line. If you had some variable D that maybe wasn't an unsigned char and you wanted to get its value and convert it to that, you can put unsigned char inside parentheses and it'll do the type conversion for you. You've noticed in C, a lot of types have kind of multi-part names like long double. In cases like that or unsigned char, you just put the whole name inside parentheses. Remember, typecasts have very high precedence. That was on our precedence chart up at the start of the lecture. So it means if you've got a typecast like this and maybe you had a bigger expression out here after it, unless you put parentheses around that expression, the typecast is probably just going to apply to the first thing in the expression, again, because the typecast has such high precedence. I'd say keep that in mind because otherwise it's easy to think you're typecasting the result of a big expression when you're only getting a typecast on the first thing in that expression. There's one more place where you can use a typecast in C that I don't think Java cares about this. But if you call a function and it's not a void function, meaning it returns a value, but you don't need the return value, you can put a void, a typecast to void in front of it. Like I'm calling this function f, and then I'm casting the result to void. And that's just telling the compiler, I don't need the result of what this function returns. Even if you didn't put the void, if you don't do anything with the return value, the compiler knows that you don't plan on doing anything with it. But in some cases, it might generate some warnings letting you know that you're not using the return value. And this casting to void can be a way of suppressing those compiler warnings if you secretly know what you're doing and know that it's okay to ignore that return value. So here's, again, one more case where you can use a typecast in C. So that's how you do explicit type conversions. Again, it's a typecast, and you can put typecasts in anywhere you want in the expression. But like I said, in C, even if you don't do casts, in a lot of cases, the compiler will do the type conversion for you. And these are called implicit type conversions. Java would do that also, but C does it in a lot more situations. I'm showing you here what I mean. If you had an expression and it was full of a bunch of different types, like an unsigned char times a short, and then you take that result and add it to a float, and you take that result and assign it to a double. To evaluate this expression, the compiler is going to have to convert some of those types. And we're just going to try to understand the rules for how it's going to convert those types, especially if we don't help it out with any type conversion. There's a name for these rules. It's down at the bottom of the slide. It's called the usual arithmetic conversions. So for numeric expressions, ones that are doing arithmetic numeric computations, what are the rules for what type conversions the compiler is going to use? So we'll start on kind of a multi-slide trip trying to talk about this. And then at the end, I have some examples that we can work out just to try to help you make sure that you understand this. Over on the right, I've got a picture of all the different types, the fundamental types built into C. So we're really talking about the conversion rules the compiler will put in between those types. First, I'm going to try, or as I talk about these, I'm going to try to talk about them in general. What does the standard say should happen on any C compiler? And then we'll also talk about, well, what does that mean for the common platform? Because when they wrote the standard, they had to worry about, systems like our common platform and potentially other systems that hadn't even been built yet. So we'll talk about these rules again, both in general and what they mean for our particular system. When we think about types, I used this term earlier, we tend to think of them as having varying capacity. Some types like bool can just hold one of two values, whereas long double, we said that's an 80-bit value. It can hold a whole bunch of different values. We usually describe the different capacities as some types being narrower, meaning they don't support as much capacity, and some types being wider. And here's how we think of the width of a type in C. In principle, the floating point types have the biggest capacity. Well, honestly, a float can't actually store as many values as a signed long. Signed long takes more memory, but the float is made to hold, a big range of values. So we treat it as if it has more capacity, even if, like I show in my picture, it doesn't even use as much memory as some of these narrower types. So we use that word when we're talking about how the conversions work. And again, we'll think of the width of a type as matching this picture. The floating point types are wider than the integer types. And among the integer types, some of them have more capacity. Bigger ones like long have more capacity than ones like char. We're going to talk about a number of specific rules. I think we've got 4 or 5 of them, but they all follow, I think, 3 general principles, and I've listed those here. If you're writing an expression and you do an operation like multiply between values of 2 different types, like let's say you multiply a double times an int, the compiler is going to have to convert one of those, at least one of those types, just to be able to do that multiply. One rule it's going to use in principle is if one of those types is wide enough to hold the value, that's what I mean by good enough here. If it's wide enough to hold all the values that the other type could store, then just use the wider of the two. So if the wider type is good enough, just use that. We'll see there's one special case rule that says if you're doing math, bring everything up to int before you do that. When you're actually doing operations on multiply or add, don't use those smaller types, convert them to int to do the math. And then the last one is if you've got a mix of signed types and unsigned types, and they're both the same size, favor the unsigned type. Use the unsigned type instead. So given that those are kind of the logic behind these rules, let's try to talk about the individual rules. The first, and this one is a lot like what Java does. If you've got two operands and at least one of them is a floating point type, then convert to the wider floating point type before doing the operation, before doing math. That's what I'm trying to show in this picture. So for instance, if you've got an int times a double, convert the int to a double and then multiply two doubles to do the multiply. Even if you have two floating point types, use the wider of those two types. So if you had a float plus a long double, convert the float to long double and then multiply or add two long doubles to do the math. So again, if you've got a mix of floating point, or sorry, if at least one of your types is floating point type, then convert the other one. Sorry, let me try to say this right. If at least one of your operands is a floating point type, then use the wider floating point type to do the math before, or convert to the wider floating point type before you do the math. I've got a number of examples of this. I'll go through these real fast, but these are examples of the rule that we just talked about. And I think we may have said some of these. So if you have an, on the previous slide, so if you have an int times a float, well, float is the wider type, so convert the int to a float before you do the multiply, and then multiply two floats. If you've got a double plus a char, well, double is the wider type, so convert the char, the unsigned char to a double, and then add those two. If you got a float minus a long double, well, long double is the wider type, so convert the float to long double, and then do the subtraction. I think this is probably the easiest rule to remember. This is a lot like what Java does automatically. Questions before we move on? So like I said, I think we've got about 5 of these rules. This is the first of those. And it kind of simplifies our chart now, because if either of our operands are one of these top 3, we know what's going to happen. So all that's left is, what if they're not? What if I have 2 different types drawn from this bottom part of the chart? The C language defines rank for talking about integer types. It's the same idea as width. It's just the word they use to talk about the size of an integer type. So larger integer types like signed long are higher rank than smaller ones like char. So I've drawn these arrows to show how rank varies as you move between these integer types. And some of these rules talk about rank. And I kind of already said this one. This is just officially where I'm supposed to talk about it. If one of your operands has a lower rank than int, so if you had one of your operands was a short or one of your operands was a char, then promote it up to at least int before you use it in an expression, before you do math with it. So the idea is when you're actually doing a multiply or divide, the compiler is going to plan on doing that with a type that's at least the size of int. You can still go back and store the result in a smaller type, but to actually do the mathematical operation, it'll use a type that's at least int in size. And that's what I'm trying to draw with this picture. If either of your operands, or if both of them, are smaller than int, it'll bring them up to, it'll convert them to at least int size before it uses them in a math, before it does math with them. On the common platform, the int type is large enough to hold any value held by the lower rank types. That's what I'm trying to show in this picture. If you had a value in a signed short, That same value would easily fit in a signed int. If you had a value in an unsigned short, that would also easily fit in an unsigned int. So on the common platform, for any values smaller than int, they're always going to be converted to signed int.
I'm sorry, I've got
Sure.
a quick question.
Sure.
Oh, geez, I'm sorry. I just now realized I thought you were saying unsigned ints would also be converted to signed ints, which I thought would cut them off.
Right. Unsigned. So the rule says bring them up to at least int, but if they're already at int size, it doesn't necessarily have to bring them higher, at least not according to this rule. So again, I think this picture makes sense. I think this is how the common platform works. For any of those types that are smaller, anything they could have held could fit in a signed int, so it just converts them all to signed int. Why am I making a big deal out of this? Well, not all platforms are going to be like that. Some platforms, a short could be just as big as an int. That'd be a little weird, but on some systems, maybe a short is also 32 bits, like my picture shows. On those systems, bringing a smaller or lower ranked type up to int wouldn't let you always go to signed int. And that's what I'm trying to show on this picture. If you had a system, and again, the common platform's not like this, but if unsigned short was just as big, took just as much memory space as int, if you converted an unsigned short to an int, you would get overflow. So in that case, it's converted to the integer size type that can hold its value, which would mean unsigned int. It would stay as an unsigned int because signed int couldn't necessarily hold the value stored in an unsigned short. That would only be true if unsigned short was just as big as an int. If you rewind, common platform's not like that. It's easier to think about. I think it makes more sense to me, but there could be a system like this out there. And then their rules for conversion would be a little bit different. Here I'm trying to do what I said I would do. I'm trying to describe what the standard says. It says bring the value up to at least integer rank, but that may not always mean you can convert to signed integer if, say, signed integer wasn't big enough. I've got some examples here, and we'll pretend we're on the common platform, so that's the picture I put down here. Oh, but these are all easy, because the rule for smaller ranked types, for lower ranked types, is just bring it up to int. So if you multiply a char by an unsigned short, those are both going to get converted to int, at least to do the multiply. If you add a bool to a short, well, bool is still an integer type. It just holds values 0 or 1. So both bool and the short will get converted to int. If you subtract an unsigned char from a char, they'll both get converted to int before they're doing the subtraction. Questions before we move on? All right, we're getting through our rules. And as we do, our type chart gets simpler, because now we know everything that happens if one of the operands is from up at the top, and we know what happens if the operands, at least if both of the operands, are from down at the bottom. So now all we have are these middle 6 types. And so what happens if you write an expression made of just those types? How will the operands get converted? Well, as long as they're the same signedness. So if you're adding 2 signed values or 2 unsigned values, it's kind of like our first rule. It just uses the wider or the higher ranked value of the 2 operands. Do I have examples? And these are so simple, I don't have examples written down, but I can make up one. So if you add a long to an int, well, they're both signed, so it'll convert it to the signed long. If you add an unsigned long to an unsigned int, well, unsigned long, that's one of these and one of these. The unsigned long is the wider type, the higher ranked type, so it'll convert to the unsigned long. So now the only thing we have left is, what if you mix signedness? What if you have one operand that's signed and one operand that's unsigned? So you're getting a type from either side of this part of the chart. Well, there's 2 rules left for this. And the first one is kind of like that first rule I started with when I was kind of describing the ideas behind these rules. If the signed type is good enough, if it is able to hold any value the unsigned type can hold, then just use the signed type. And that's what I'm trying to show with this top picture, although I don't know if my picture works as well. If you have, we'll do an example. If you have a signed long times an unsigned int, well, signed long is so big, it can hold anything the unsigned int could have held. It's got bigger capacity. So in that case, it'll convert the unsigned int to the signed long, and then it'll do math on two signed longs. So again, the idea is if you've got a signed operand and an unsigned operand, and the signed one is big enough to hold anything the unsigned one could have, then it'll use the signed operand. On Common Platform, we already saw that long is secretly no bigger than long. So signed long could hold everything an unsigned int can hold, but it can't hold everything an unsigned long or an unsigned long can hold. So this rule wouldn't apply if you were multiplying a signed long times an unsigned long. I'm sorry it sounds so silly for me to say those type names. That's one reason I'm pointing to this chart as I do it. Other platforms could have a long type that was even bigger than long, in which case they might have cases where an unsigned long would be converted to a signed long to do math, but our Common Platform wouldn't do that. Questions before what I think is our one last rule? All right, so this one says if the signed type is big enough, just use the signed type, if it can hold everything the unsigned one could. What if it's not? That's all that's left. You've got an expression and you're, let's say, multiplying an unsigned value by a signed value, and the signed value is no bigger than the unsigned one. Our last rule says favor the unsigned type. Use the unsigned version of the higher ranked type. So that's what I listed up here. I tried to make a picture that shows that, and to talk through my picture, if you're multiplying, for example, if you're multiplying a signed int times an unsigned int, well, the signed int is no bigger than the unsigned int. So in that case, use the unsigned type. Convert the signed int to an unsigned int, and then multiply two unsigned ints. Same here if you've got a, yeah, I'm just trying to think of, I think it's on my next slide, but I'm trying to think of an interesting case. If you've got a signed long times an unsigned long, well, on the Common Platform, the signed type is actually no bigger than the unsigned type. So the rule says in that case, use the unsigned version of the higher ranked type. So in that case, both operands would get converted to unsigned long to do the expression. Again, like I've said a couple of times, I think of this as a rule being all else being equal. If the types are the same size in memory, use the unsigned type rather than the signed one. This may seem weird. I guess we have to favor one of the two types. Why would we favor unsigned rather than signed? The way I remember this is I think of, well, if you're using an unsigned type, you're using it for a reason. You chose unsigned because you needed more capacity on the positive side. So given that you chose to use unsigned, if you do math with mixed signedness, with a signed value and an unsigned value, it's going to favor the unsigned type you're using. I've got an example down at the bottom that kind of shows how this can make sense. I made a variable x that's signed, and then I go through and I keep subtracting 1 from it. Well, technically, that x it's this variable, so it's an unsigned int. That plain old 1, I didn't say anything special about it, so it is a signed int. Again, if I'd put a u at the end of it, the compiler would know I meant unsigned, but since I didn't, the compiler is going to see this and say, oh, you've got an unsigned int minus a plain old int, a signed int. How should I do that math? Well, this rule says it's going to convert that 1 into a unsigned value before it does the subtraction, which is probably what you want. If you wrote this expression, you probably want that math to be done as an unsigned value. So again, I think of this as all else being equal, favor the if you've got a signed and an unsigned type that you're doing math with, and they're equal size, favor the unsigned one. I've got some question.
So with that arithmetic you carried out on that code,
yeah.
If you added parentheses to encapsulate the -1 and just had a plus for it, would it still take it as unsigned?
Yeah, so
like
you're saying you put a
-1?
plus between those, and instead of that being a minus, you mean for it to be the negation operator.
Yeah.
It will still follow this rule, which may seem silly. You might say, well, why would you want to take a -1 and turn that into an unsigned value? But it's generally not looking, when it's figuring out the type to use for an operation, it's not looking at the value you're doing math with. It's looking at the type. And that's really what we're talking about here. I know it seems silly to look at a -1 and say, oh, I'm going to make that unsigned. But most of the time, if you're writing an expression with operands, you probably don't know the values of those operands. If you're adding two variables, the compiler might not know what's going to be in those variables when it writes the code to do the math. So it's got to pick a rule that makes sense no matter what value is there. Here, if you turn that -1 into a real -1, maybe that doesn't look like it makes as much sense, but the compiler is still going to apply the same typing rule. You've got an unsigned int plus an int, which happens to be -1. It'll say, I'm going to convert that int into a signed value before I do the math. That may not be a satisfying answer. I think it's an accurate answer. Did that kind of answer your question?
Yeah,
all right.
Thank you.
So again, even though there's just a plain old number there, these rules would also apply if everything was a variable, in which case you wouldn't really know what value it had. So I've got some examples here, and here I'm trying to show off those last two rules. So if you got a long times an unsigned int, well, the long is big enough to hold everything the other one could hold. So it's going to convert the unsigned int to a long before it does the math. If you've got an int plus an unsigned long, it's kind of the other way around. The int type is not big enough to hold everything the unsigned long can. So here it's going to favor the unsigned type. It'll use the unsigned version of the higher ranked type, which here is just going to be unsigned long. So it'll convert the int to unsigned long. This last one I think is maybe the only the only interesting case here. You've got a long minus an unsigned long. Well, on the common platform, long isn't actually big enough to hold everything the unsigned long could. So it'll use the unsigned version of the wider type. The wider type is long, so it's going to convert both of them to unsigned long before it does the math. I've got some more examples here. Let's talk through these. Here I made up three variables. I tried to give them names that made them easy to remember. So that there's a float f, there's an int I, and there's an unsigned character uc. In that first expression, int plus I plus uc times f. Think for a moment of any conversions it's going to do. When that plus gets evaluated, what types are its operands going to be? Anyone want to give it a try?
It'll be in a float because the float's the biggest one.
So that's worth thinking about. And it's correct, but I want to sneak up on it a little bit. This plus is way over here, and the float isn't its operand. It's an operand of times. But to figure this one out, and this one's probably a little bit tricky, you have to think about precedence. And this plus isn't so I'm only asking about this plus. but it's not the first operator that's going to get evaluated. First, it's going to multiply the float times unsigned char. So it's going to convert the unsigned char to float so it can do the multiply. So then by the time the plus gets to evaluate, the operand on this side is going to be a float, the operand on its right, and its left-hand operand is going to be an int, so it's going to convert the int to a float before it does the addition. And again, that's because this multiply is going to happen before the add. So maybe that was a tricky one, but it's worth thinking about that. In this next example, you've got a signed char times a short plus a long int. Well, here the multiply is going to happen first. These are both lower rank than int. So on the common platform, they're both going to get promoted to int before it does the multiply. Stop me if you have questions about this. Here, I've got a divide and a multiply. These operators, they have the same precedence, so they're going to evaluate left to right. Signed char divided by unsigned int. Well, it's going to bring signed char all the way up to int, but now I've got a int divided by an unsigned int. They're the same rank, so it's going to favor the unsigned type. It's going to convert that to a unsigned int before it does the divide. So now on the left, you've got an unsigned int. On the right, you've got a long int. Long is big enough to hold everything an unsigned int can hold. So it's going to convert the left-hand operand to long before it does this multiply. So the answer for this one is long. Down here, this last one, I think this is what we started with. And if we wanted to answer for all of these, this one's actually kind of easy. I should come up with a better example for this. You got unsigned char times short is going to happen first. Those are both going to get promoted to int to do the multiply. And then once that's done, you'll have a float plus the int result from here. Now, the float is a floating point type, so it's going to promote that int result to a float before it does the add. And then we haven't actually talked about this. What happens during assignment? I think I've got a slide for that. For assignment, the implicit conversion rules are really easy. The compiler will just convert to the destination's type so it can do the assignment. In Java, if you're assigning from a wider type down to a narrower one, Java makes you do a cast there to make sure you know what you're, to let you prove that you know what you're doing. But here, even without the cast, the compiler will still let you do this. When I multiply a char by a double, it converts the char to a double, does the multiply, and then the result on the right is a double. But it'll let me assign it to an int without even a cast. It'll, like we already talked about, it'll discard the fractional part and then assign it into an int, possibly with some overflow. I gave some examples. We talked through them real fast. Any questions before we move on and talk about some other type conversion rules? All right, so we just talked about what happens when you do an assignment, and there I think the rules for implicit conversion are easy. How about when you call a function? When you call a function, it seems like two things can happen. You have to worry about, well, what if I pass in some types that don't match the parameter types? Here, since C does not let you do overloading, this is also kind of simple, kind of like assignment. If I define a function that says it takes a double and a bool, and then I call it with two different values, say a char and a double, well, since this function has to take values of these types, the compiler will automatically convert so that it can call the function. So this char will get converted to a double, and even this floating point number will get converted to a bool. Same thing happens on return. When a function returns, it might return a value, and then if the value it returns doesn't match its return value, like here, x minus 1.0, technically that's going to be a double. But if you say your function returns an int, it'll automatically do the conversion for you, because the only thing this function can return is an int. And then on the other side, when you take that return value, if you assign it to something that's of a different type, we just covered that rule, that's just assignment, and the compiler will convert to the destination type. So implicit conversion can happen on the parameters to a function call and on its return type. That's all I've got to say about type conversions. I know we covered a lot of stuff, hopefully quickly. Any questions before we move on and talk about flow of control?
Yes, sir. When you're
Sure.
converting the booleans, is it just converting any positive number to 1? So if you were to take the value of that y?
Yes. So yeah, so like when I pass in this 3.14 as a truth value, that is true. It's non-zero, so the compiler treats it as true. So when this bool shows up in this function, it should have a value of 1. The only case it wouldn't is if this was a floating point 0. Other questions? All right, flow of control. These are just, branching and looping statements. We already talked about these briefly, so I'm mostly just going to talk about how things are different in Java, some things that we haven't talked about yet. And one way they're different is the logical operators. Logical negation, logical and logical or were defined in the original version of the language before we even really had a Boolean type. So just like Booleans, they work on integer values. That means if you give them an operand that's not an int, or at least the compiler will convert to int before it does these operations. And these operations result in an integer value. You can, of course, you can assign that to a bool result, but if you want to talk about the type of what these evaluate to, it's always going to be int. So I made up some examples here. I made an int and a float. If you just wrote down I, the integer variable, its type would be int. If you multiplied it by a float, we just covered that. It's going to promote the int to a float so it can do this multiply. So the result of this is going to be a float. But then if you take that result and start using it in one of these logical operators, like if you take that float result and it with another float result, it'll convert both of those to int, so it can do the and. And also, the whole thing will evaluate to an int. So the type of this expression, even though it's got floats in it, the end result is going to be an int. Again, because these operators all evaluate to int. While we're talking about operators, just like in Java, the logical and logical or operators are guaranteed to short circuit. That means if the left-hand operator kind of determines the result, it won't even bother evaluating the right-hand operators. I'll mention quickly, probably they told you this in Java class. You might think this is for performance, and it does have a small performance advantage. It saves you a little bit of work, but I don't think that's the right way to think about it. I think it's better to think about these as giving you a good way to structure a conditional so that the parts of the condition on the left can protect parts on the right. And that's what I'm showing down here at the bottom. Here, I'm pretending you have a number of people and a number of pizza slices, and you're trying to decide if there are enough slices for everyone to get at least one slice. And one way to do that is just to divide the number of slices by the number of people. And that works great unless there are 0 people, in which case that would be a divide by 0. And you wouldn't want to do that because that would crash your program. So in that test, I structured the conditional. So I've got a kind of some people call this a guard out here on the left. First, I check to make sure we have at least one person. And if that's true, I bother doing the division. Because of the short circuiting, this part of the conditional won't even get evaluated if people is 0. And that's probably what I want, because if it was evaluated, that would be a divide by 0. It's easy to get in the habit of writing your conditions like this so that kind of parts on the left protect parts on the right. And again, that's kind of what I think of this short circuiting trick as being primarily for. Talking about expressions, there's a special type of expression in C called a constant expression. Sometimes I call this a compile time constant. And that just means the expression has a value that the compiler can figure out before it even runs your program. So an obvious thing for that is if you had an expression that was just the number 3, that's a constant expression. It's just the plain old number 3. The compiler can tell what that value is, even if it was a little more complicated. like 3 times 7. Well, if it's just made of constants, the compiler can figure out its value during compilation. So that's what a constant expression is. It's one where the compiler can figure out the value of that expression, what it's going to evaluate to while it's compiling your code. Why does this matter? Why do we care about constant expressions? There are a few places in the language where you have to use a constant expression. So we have that term so we can talk about those places. One place is the case values on a switch statement. They can be plain old, so they all have to be constant expressions. That could mean you could have a case with a plain old number like 0, probably like you always would. You could have a case where the compiler has to do a little math to figure out, oh, that's just a silly way of saying 1. Even sillier, more complicated things, as long as the compiler can figure out that value during compilation, it's a constant expression and it's okay for the cases on a switch statement. Not this case down here. Here, I tried to make a case of a switch statement with a variable 3 on it. And even though we could look up and see that, oh, 3 has a value of 3, the compiler wouldn't consider that a constant expression. It wouldn't let you write a switch statement like that. I don't know if I have a separate slide for this. I don't. I may say this later, but I'll go ahead and say the reason for this. And the reason why you have to use integer values as the expression in a switch statement is because of the way the compiler plans on implementing that. If it can, it's going to implement a switch statement not as a bunch of tests. Like it's not going to write code to say, oh, was val 0? Was it 1? Was it whatever this evaluates to? Because that could be expensive. If you had a lot of cases, it might have to go through all of them doing that test. If it can, the compiler is going to implement this as a jump table. It's going to make a little array of pointers to different blocks of code. It's going to have a pointer to this first case, a pointer to this next case, a pointer to this next case. And then it's going to use whatever this value is to jump straight to the right block of code. And this can give you a really efficient way of implementing a switch statement. You can immediately jump to the right case, no matter how many cases you have. And that's really kind of what a switch statement is for in C. Under the right circumstances, it can let you write a really efficient multi-way branch. We've got a few other flow of control statements that are a little bit different from Java, so I want to talk about those. To show this off, I wrote a little nested loop program. It runs an outer loop with 10 iterations, printing 10 rows. For each row, it prints 10 things where everything is a dot followed by a star. So for this initial version of it, you should get output that looks like this. I want to use this to show off break, continue, and then a go-to statement. C's kind of most hated flow of control statement. First, we'll do continue. It's just like Java. When you execute continue, it jumps to the next iteration of the outermost loop. So if I put a continue between the dot and the star here, whenever this test is met, it'll print the dot, but not the star, because it'll go ahead and jump to the next iteration, which means on some parts of these rows, I get dots, but not stars, because I went to the next iteration of this inner loop before printing the stars. So like I said, this works pretty much just like Java. Sort of, so does break. Break is a way of jumping out of the nearest surrounding loop. So I put the same code here, but I did a break instead of a continue. So when this condition is met, instead of, it won't just not print the star, but it'll bail out of this whole inner loop. So for some of these lines, I don't get as many dot stars because I bail out early. For later iterations, I don't bail out until later, so I get a whole row worth of dot stars. Break in C is pretty much like break in Java, except you can't do labeled breaks. In Java, you can use a break to exit out of multiple loops, multiple nested loops, by having a labeled break. And C doesn't let you do that. but it's got something that's far more powerful and far worse, and that is the go-to statement. I've mentioned this a couple of times. Go-to is, well, C is an older language, and it probably has more in common with assembly language. And you'll see when you're programming in assembly language, you can jump around anywhere in your code that you want. And go-to lets you use that in a language like C. The way it works is if you're in, and I'll say it lets you jump around anywhere within the same function. To do this, you've got to put a label in your code. And a label looks like this. It's just an identifier, so like a variable name or a function name, followed by a colon. And the label is like a destination for a go-to. You can jump to it from anywhere else in the function. The way you do that is like I'm showing down here, go-to, and then whatever label you want to jump to. Here you don't use a colon. That was just defining where the label is. I do have a semicolon here because go-to is a statement. So it has a semicolon at the end, just like any other statement. So this would let you, this kind of would let you be in as deeply nested code as you want, and you could jump all the way out of it by just jumping to a label that's out of it. It would even let you jump into loops if you wanted. That seems like a silly thing to do, but you could have a label inside a for loop, and you could jump into that for loop without even really entering the for loop. That'll work. Might not work the way you want, but the compiler will at least compile code like that. You'd have to worry about, well, if you didn't go into the for loop normally, what values are your variables going to have? And they're going to behave mostly like uninitialized variables, but the compiler will let you write code that looks like this. If we wanted to simulate kind of Java's labeled break, this shows how you could do it with a goto. Whenever my condition is met, instead of doing a break, I just do a go to this label, and then I just put the label outside this loop, and whenever I do this go to, it'll jump to that label. And again, a go to lets you jump to in. Question?
Sorry. So you mentioned the go to lets us go anywhere in the code, whether or not
Anywhere
it's
in the same
initialized.
function.
Oh, I was going to ask, you said we can even use it to go into for loops.
Yes. You wouldn't want to, but you could.
What happens to the initialization of the for loop header where it like defines I as being a value?
That's what I was saying. So that I variable will exist. It'll have storage somewhere in memory, but if you didn't execute its I equals 0, it's going to have garbage in that location of memory. Or, you know, whatever, we'll talk about this later, but whatever was previously stored in that location of memory. So the compiler will let you write code like that, but it's up to you, but you probably wouldn't want to. And it's up to you, the programmer, to think about what values your variables might have if you tried to write code like that. But typically they'd have whatever happened to be in that chunk of memory when that variable got allocated.
Okay, thank you.
All right, so here's how you can use goto. Here is how you could use goto to write this same code without any structured looping. So here I'm using, at least back here, I'm using at least 4 loops to write loops. But if you got access to goto, you don't really need to even use a for loop. Here I put labels around, and I won't trace through this whole execution, but kind of this test up here is kind of, this initialization in this test is kind of like part of the for loop. I'm going to keep looping until I is at least 10. When it's done, I'll jump out of all of this code. This part down at the bottom is kind of like the rest of that for loop. Every time around the loop, I'm going to increment I and go back to the top. So it's kind of like I wrote my own ugly code for a for loop. And the same thing's going on inside here. I'm not showing you this because it's a good idea. I'm showing you this because this is kind of one of the reasons why people suggest avoiding a goto. It can really make your code hard to read and understand. And I think this is probably a lot harder to read and understand than this. They do the same thing, but using the structured looping statements and kind of knowing where execution might go to might resume after a for loop makes code easier to understand. This is really why I suggest avoiding break and continue if you can, because they have some of the same behavior. Break and continue make it so that you don't just look at the top of a loop to understand what it might do. You kind of have to look through the whole loop to see if there are any secret exits from that loop. So on your next exercise, you get to write code that looks kind of like this, hopefully just once. Hopefully you'll do that and then you'll agree, yeah, this is not a good way to write code. But goto's there in the language.
Sturgill.
Sure.
Professor Sturgill. I remember in a prior assembly language-based class, they had a similar goto, but it was limited on how far within the code it could go because of memory allocation. So it could only reach so far back or so far forward. Is that true in C? If you have a very, very large program, can you go all the way back to the beginning?
Well, you can only jump around within the same function. So you can't jump between functions. But no matter how big your function is, you can count on the compiler being able to write a goto that'll work. And I know what you're talking about with assembly. They're the only jump and branch statements we have. They're not really structured like a C or a Java program. They just let you jump around your code like this. So this is kind of a preview of what it'll be like to write a little bit of code in assembly later on. Other questions? All right, since gotos only work within a single function, the scoping rules for labels, if you think of them as having a scope, where can I talk about a label, they're kind of different from any other parts of the language. A label can be anywhere in your function and you can jump to it from anywhere else in that same function. So this done label up here is in the scope of this goto. This goto can use that done label. But since every function has, since you can only goto around within a function, every function has its own scope for labels. So even though these two labels are called exactly the same thing, they don't clash for names. They don't have a name collision because they're only meaningful within the function where they're defined. Like I tried to say, it's probably best to avoid using goto. You're gonna make other programmers angry and you're gonna look like you don't know what you're doing. There are probably a few cases where it's acceptable, maybe a good idea. C does not have an exception mechanism like Java has. It doesn't have a way of jumping out of a bunch of code to maybe get to error handling code. Sometimes you will see that handled using a goto. That's what I'm trying to show here. Maybe something bad happens in some deeply nested code and you just want to jump to some code that'll clean up and exit. You could put that code all in one place at the bottom, and then no matter how deeply nested you were in this code, if something breaks, you could use it to jump out of that. I think that's probably one of the best places where you might choose to use a goto. The other place might be occasionally. It has some performance advantages. Occasionally, instead of having a bunch of parts of a conditional that let you get out when you need to, being able to just jump to a block of code can let you handle things more efficiently. Most code is not performance critical, so most of the time that's probably not the right decision to make. But for performance critical code, you might be willing to use goto if it made your code faster. Rarely. Goto, because it lets you arbitrarily jump around code, it makes it easy to write some errors. And this is actually a security flaw that was in a piece of code. What is it? SHA. Oh, sorry, it was SSL, Secure Sockets Layer verification code. And this bad goto here made this code jump past the last test in its series of security tests, which means this test never actually got executed. And that wasn't noticed immediately, and it allowed insecure code to operate in the wild for a little while. So goto kind of introduces some new opportunities to make mistakes. We've been talking about expressions. Expressions can have side effects, meaning normally an expression evaluates to a value. It computes some number or something like that. But because we have things like pre-increment and post-increment, we can write expressions that also change things. And that's what we mean when we talk about side effects, an expression that doesn't just compute a value, but it also changes what's in some variables. Expressions with side effects can do some unexpected things, especially in C. I've got some examples of this. I guess let's take this one here. I'm pointing at it with my mouse. The second one, probably the smallest of them to talk about. Here I set a to 2, and then I've got an expression that adds 1 to a, and then adds that to another copy of a. The question would be, what does b get in this case? Well, this is pre-increment. So the value I get from a here should be a after it's been incremented. So a should get incremented to 3, and then the value I get from this left side of this expression should be a 3. But how about the value over on the right? Well, am I going to get the value of a before it got incremented? Am I going to get a 2? Or am I going to get a value after it was incremented? And pre and post increment don't really tell you that. They tell you what value you get when you're using a++, but they don't really say what happens elsewhere in the expression. And every one of these expressions is like that. I've got some side effects, like I'm adding and subtracting to a and x here. Up here, I'm passing these variables by reference, which means the functions could sneak in and change their values. If they do, when I call h, does it get a value of b after g may have changed it or before g has changed it? In Java, all of this is specified. It says if you have an expression with side effects, here's the order it's going to get evaluated. But they didn't do that in C. They left that unspecified so that the compiler had the opportunity to write as efficient a version of the code as it could for expressions like these. But it means for most of these expressions, it may be impossible to say what they should evaluate to. The standard leaves that unspecified. That just means as the programmer, it's up to you to worry about this. If you're writing an expression that includes side effects, you need to think about whether or not you're even guaranteed what value it's going to evaluate to. There are a few places where the compiler does make guarantees about evaluation orders. And that's what we call a sequence point. A sequence point is a place in your code that we can point to, and we can say, at this place in your code, everything that has happened before or all the expressions that come before this, any side effects they have will have already taken effect before the stuff to the right of this sequence point, before the stuff after it. And like I said on the previous slide, the C specification gives the compiler a lot of opportunities to write code for an expression the way it wants, which means really there are few sequence points in the language. And I've listed them here. The semicolon at the end of a statement is a sequence point. One statement does its thing before the next statement. In a conditional, the closing parentheses for nesting or at the end of an if statement, at the end of a conditional in an if statement, that's a sequence point. Same with just about all of the logical operators. The and operator and the or operators are sequence points. So here, for example, if A was an expression that had side effects, those are going to take effect before B even gets evaluated. Same with a ternary operator. Any side effects in the condition happen before the two remaining expressions get evaluated. Even the comma operator we learned about before is a sequence point. And there are a few others. If you call a function, any side effects in evaluating the parameters occur before the function executes. Same thing with return. If you return from a function, any side effects in computing the return value, those happen before the function returns a value. Since there are so few sequence points in the language, like I already said, it's up to the programmer to worry about this when they're writing code. We got one big-ish topic left today and not a whole lot of time. So we'll get through it. We'll get through as much of it as we can. We may have to leave some of it for next time. Any questions before we start talking about functions? So you already know how to write functions. You're using a lot of your knowledge from Java there. I want to touch on maybe some specific C things with working with functions that we haven't talked about before. Functions are important in C because kind of in Java, objects, classes are our biggest building block for writing code. In C, functions are the biggest thing we get to write. So we want to talk about kind of policies for what our function should be responsible for, how we should break up a program into multiple functions. There are a few details. When you're writing a function, it can have parameters and it can have a return value, but it doesn't have to. You can have functions that have no return value, in which case you just mark them as void returning functions, just like in Java. If they don't take any parameters, you can put the word void inside the parentheses when you're defining the function, and that's a way of saying this function doesn't take any parameters. In C, if you just leave that blank, officially you're saying, I'm not going to tell you anything about the parameters of this function. So officially, if we have a function that doesn't take any parameters, we should be putting the word void there inside parentheses when we're defining that function. Even functions that don't take parameters or return anything, they can still just do something useful. This abort function terminates your program. It doesn't need to know anything. It doesn't return anything back to you. It just terminates your program unsuccessfully. So it's an easy way to just stop your program when you have to. Functions, go ahead.
Apart from the void, I know we talked about earlier with casting and how things will just automatically be casted. Does the return part in the header actually do anything, because it'll pretty much cast to whatever you do end up returning?
So you mean if I wrote a function like this and I said this is a void returning function, do I need to say it's void returning? Is that what you're asking?
Well, I mean, like if you wrote a function that says it returns an int, but you had it specified to return in your code a double, and it just automatically gets casted. Did the header really do anything? Would it even matter if you specify between int or double if it's always going to cast?
It is important there, because if you didn't specify this is an int returning function and you tried to return a double, the compiler wouldn't even know that it had to convert that. So saying this is an int returning function tells the compiler conversions it might have to do when you return. It also helps you catch if you forget to return. Depending upon the warnings you've got turned on your compiler, if you write a piece of code and then at the bottom of your function you just forget to have a return statement, you'd like to have a warning about that. If the compiler thought it was a void function, it wouldn't warn you. But if you said this function is supposed to return an int, and there was a path through the function where it didn't return anything, at least the compiler can let you know about that.
Okay.
Other questions? All right, so I was trying to say, when you're calling a function, just like in Java, we've really got two words for the parameters. When we're defining the function, the names we give to the parameters, we call those the formal parameters. So X and Y, those are the names for whatever you pass into this function. Again, those are called the formal parameters. There are names for the parameters inside the function. I've probably said that enough. When you call the function, you have to supply values for each of those parameters. And just like in Java, we call those the actual parameters. So in this example, X and Y are our formal parameters, and 7 and M are our actual parameters. The 7 is going to get converted to a float, and the M is going to get converted to a long when I call this function. When you call a function, the compiler wants to know, at least in C99, the compiler wants to know its formal parameter types and its return value types. And the reason for that is so that it can do the conversions we were just talking about. Here, I've got a function that takes a float and a long. If the compiler doesn't see a definition of that function until after you've already called it, The compiler is going to write code for this call, and it's not even going to know that A, the 7 needs to be converted to a float. And it's not going to know that this B, this M, needs to be converted to a long. So for this reason, the compiler wants to see a definition of your function before it sees a call to it, at least C99 does, so that it can do the right parameter conversions and the right conversions for the return value. Compiler isn't assumed to be smart enough to look at all of your code at once. It's kind of trying to, at least it's designed so that it could be trying to compile your code as it sees it. Let me get in this topic and then I'll say that we're out of time, so we'll call it a day. To do this, I said you can put a definition of your function before any of the calls, and then when you call the function, the compiler already knows what the function looks like. Or you can use what we call a function prototype. A prototype says what the parameters and return type of the function look like without giving a definition of a function. So a definition of a function looks like this. It's got a body of a function inside curly brackets, and this is what you've been writing all along. A prototype looks like this. It looks just like a function definition, at least the header, except instead of having a body, it just has a semicolon. This tells the compiler, oh, there is a function named expunge, and it takes a float and a long and returns int, but I guess you didn't tell me what its definition is. I hope you're going to tell me about that later. So for functions that you prototype, the compiler knows what they look like, but you're going to have to, at least knows what their parameter and return types are, but you're going to have to put a definition later in your code. Let me get through 2 more slides. I'm probably cheating you by a minute or 2. There are a few places where this distinction shows up: a definition versus a declaration. A declaration tells the compiler about some identifier, either a function or a variable, and it tells you its type, but it doesn't tell you everything about it. For a function, it doesn't give you the body of the function, and for a variable, it doesn't reserve space for that variable. A prototype is just one example of a declaration that's not a definition. It tells you about a function, it tells you its type, but you're going to have to give its definition, give the body of the function later. Using prototypes gives us more flexibility in how we organize our code. If you wanted to use a function somewhere and then define it lower in your code, you could do that. You would just have to put a prototype up earlier. And lots of people program like this. They might have a main up near the top of their .c file. They might have a bunch of prototypes up above that, and then they might go in and define those functions later. And let's stop right about there. We've still got, I'll save this for next time, but we'll pick up right about here next week. Sorry for taking a couple of extra minutes. I'll see you on Wednesday of this week. Good luck until then.
Thank you.
Professor Sturgill?
Yes, I'm still recording.
Do we have enough? It's fine. Do we have enough?